Good day. This is Robert Kleinberg speaking to you from Cambridge, Massachusetts. And the topic today is methane emissions from the oil and gas industry of the Russian Federation. Many of you are probably somewhat familiar with methane as a greenhouse gas. It's been a popular topic for the last few years, but just to make sure we're all starting at the same place. I'd just like to point out that there are both natural and anthropogenic sources of methane. They are about of equal sizes. The natural sources, which are shown in green on this pie chart, are basically wetlands, seeps of oil and gas, and melting permafrost and other natural sources. That's about half of the total methane that goes into the atmosphere every year. The other half is anthropogenic. And the most interest has been focused on the fossil fuel sectors, which are oil and gas in red and coal in black. The reason is it's pretty easy to understand why fossil fuels have attracted a disproportionate share of interest. Firstly, methane is a primary constituent of natural gas, which is a valuable and widely marketed fuel. Secondly, under certain assumptions, some methane mitigation measures pay for themselves in addition to their environmental benefits. Thirdly, oil and gas supply chains are mostly managed by large industrial organizations that are technically sophisticated and well capitalized, so very capable of dealing with their methane problems. In contrast, emissions from natural sources, agriculture, and biomass burning are deemed harder to control. Now, one point that's very important to make is that controlling methane is the quickest way to mitigate global warming. And this was pointed out 10 years ago by Drew Shindell in an article that he published in Science. What I've done here is I've taken 3 of several cases that Shindell shows. Firstly, there's the reference case shown in red on the chart on the left, where the horizontal axis is time in years from 2010, which is when Shindell was preparing his paper, into late in the 21st century. The vertical axis is temperature change since more or less pre-industrial times in degrees centigrade. And the reference case basically takes the energy trends as projected by the International Energy Agency and agricultural trends from the Food and Agriculture Organization, projects that out into the next century. And in those scenarios, greenhouse gas concentrations in the atmosphere more than double from 2000 to 2100. So it's a large increase in greenhouse gas load. And as you can see, the temperature continues to rise at its present rate all the way through the century. It's kind of a scary proposition. The blue line is a program of carbon dioxide only reductions. And here Shindell used the IEA 450 CO2 equivalent scenario with CO2 atmospheric concentration generally flat for the next 200 years. And this is quite a bit better than what we're doing today, but it's not the most aggressive scenario you can imagine, but it's a kind of middle of the road scenario as we would consider it today. You can see that in the long run, the temperature does tend to level out. That's a good thing, but that only happens more than 30 years after this program is implemented. So in other words, from now till 2050, even if we are, pretty conscientious about reducing our rate of CO2 emissions, we're not going to see any change, any mitigation of global warming by 2050. Now, the third line, which is in green, is methane-only emissions. And those are emissions from the fossil fuel sectors, municipal waste and landfills, agriculture, and so on. And the model here is that methane emissions are reduced linearly from 2010 to 2030 and then held constant. Here, you get pretty much instant response from the Earth's temperature. Green departs from red kind of right away as soon as you start this program, and continues departing as long as you're reducing emissions. Now, once the reductions start and you sort of level out and have constant emissions, then the green line will once again track the red line, the reference case. So really, for the best possible outcome, you need to reduce both carbon dioxide and methane. That makes sense. But surely, if you want to see any mitigation of climate change by 2050, methane has got to be an important part of that story. Now, the amount of methane going into the atmosphere is tracked by the UN Framework Convention on Climate Change. And every year, the Annex 1 nations, which are the more industrialized ones, submit national inventory reports to the UN FCCC. The countries, in all cases, use what is called a bottom-up or emission factor inventory method. And the way this works is that you make a list of your emitters, and in the oil and gas case, that would be various phases of production, transport, storage of fossil fuels. And each one of those sectors in the oil and gas industry is assigned what's called an emission factor, which is the mass of methane emitted per unit throughput of fossil fuel in that segment. That emission factor is multiplied by what's called an activity factor, which is the annual throughput through that segment. So, for example, if you're producing gas, you know exactly how much gas you're producing, generally speaking. That is multiplied by an emission factor, how much gas you lose in the production process. And then all those different contributions, the production, transport, storage, and so on, are then all added up. And so it's basically a spreadsheet exercise that does not depend on measurements. That's an important point. Now, the Russian government reconsiders its slate of oil and gas emission factors almost every year. And the changes in the emission factor it assumes can be very, very large. So, but once the emission factors are changed, then they are applied retroactively to the whole history of methane emissions, going back to 1990, which is when this protocol started. And that's why you get these lines on the chart on the right that are sort of track each other. They all have common activity factors, but the emission factors have changed in each report. And you can see they've changed by very, very large factors. So, for example, from the 2016 report to the 2020 report, the methane emissions in a given year have fallen by a factor of 6 to 8. So these are very, very large changes. Now, the United States uses a similar system, whereas the Russians have about 15 or 16 different segments they track. In the United States, the EPA tracks 250 different methane emission sources. So it's much more granular, and the changes are much more cautious. So you do not see these big changes from year to year. Now, this has had a really profound effect on sort of the image, you might say, of Russian industry versus American industry. So, for example, in 2013, the Russian Federation reported methane emissions of 32 million tons from its oil and gas industry, representing a methane intensity, which is methane emission divided by dry gas production, of 7.4%. By 2019, 16 years later, they decided that just by changing emission factors, the methane emissions had declined to 4 million tons, a factor of 8 lower, with an emission intensity of 0.8%. And at this point, they now look better than the United States, which has a larger oil and gas industry. It emits 8 million tons of methane a year, according to EPA estimates, with a methane intensity of 1.2%. So now, are the Russians really better than the United States? I'd say we don't know, because these changes from year to year are very large. It doesn't give you much confidence that the Russians are kind of playing straight. So one thinks, okay, we have methane detecting satellites. Everyone's heard about that. And so perhaps we can use satellites to sort of reveal what's actually going on in these various countries. And so the data from Russia is shown here on the right. The black dots are total methane emissions from all sources, anthropogenic and natural. The blue dots are the anthropogenic sources. The green dots are natural sources, and red is fossil fuels, which is a subset of the anthropogenic sources. Now, all the dots represent 11 different processing schemes used by different groups using different assumptions, all using the same data, which is GOSAT data from 2017. And so you might wonder, well, why are all these processing methods so very different? Well, the reason is that, and this is very important, there's nothing inherent in satellite data that distinguish natural from anthropogenic sources, nor fossil fuel sources from other anthropogenic sources. So we have to use an inversion method. Moreover, satellite measurements are compromised by clouds, surface albedo uncertainties, such as wetlands, snow, water, and poor lighting conditions, which is very prevalent in the Arctic, especially in the winter. And there's large parts of the Russian Federation that are cloudy, that have a lot of wetlands and snow, and are in the Arctic. So these are real problems that make satellite measurements more uncertain. Now, modern inversions use the Bayesian method, which is initialized with a set of priors. And the priors are sort of initializations and representing your best guess of the outcomes, which are called posteriors. Now, as Marielle Sanois said in one of her giant surveys of global methane emissions, quote, atmospheric inversions use bottom-up models and inventories as prior estimates of the emissions and sinks in their setup, which make bottom-up and top-down approaches generally not independent. So in other words, the results that we get from satellites are very much influenced by the inventories, which now we view as somewhat suspect. So satellites are not necessarily the answer. They are getting better. I mean, year by year, almost month by month, but I would say not there yet in terms of being able to validate these national inventory reports that are submitted to UNFCCC. Now, there is another approach, which I think is more promising, and that's using aircraft. So this image here comes from the Environmental Defense Fund, which commissioned a series of flights over the Permian Basin, which is America's largest oil and gas producing region. And this is in southeastern New Mexico and West Texas. Each dot is a methane emitter from an oil and gas site in the Permian. They're color-coded according to emission rate and geotagged according to the owner and operator of that site, that asset. So here, you can see exactly where methane is coming from, how much, and who owns it. So this to me is kind of a roadmap for how you might regulate this industry. And certainly, I believe, a very good, reliable method for determining how much methane is coming from any given area. So with that, I'd just like to close with some conclusions. First, A principal challenge is understanding the scale of the methane problem. Inventory methods, which are used universally, are known to be inaccurate. The biennial reports of the Russian Federation dramatically illustrate the instability of inventories. Second, it's a time-worn adage that you can't manage what you can't measure. And measurements in Russia and other countries, including the United States, have been virtually non-existent. I mean, the United States more than other countries. However, technology has been improving and the industry now has the measurement tools that can economically achieve the spatial and temporal granularity needed to have a meaningful impact on the methane emission problem. So with that, I'd like to close. I have some references for further reading shown on the last slide here. This talk is being recorded and will be available to you to review, so you don't need to write down everything right now. You can always contact me at my email address shown in red at the bottom. So with that, thank you very much for your attention.